Okay, so we've seen graphs of log of y versus t, log of y versus x. We talked about it to some extent in our last class, and this is going to be the homework in the last section of the chapter. And this is very important stuff, okay? So, for example, okay, just a little terminology we didn't use before. Semi-log graph is a log of y versus t. Okay, we saw that last time. And we also looked at log of y versus log of t, which gives us a power function. So, it's a log of y versus x, or natural log of y versus x, or log base 2 of y versus x, but it could be t, whatever the variables are. It'll have the log this way, whatever base you want to use, and t this way. Okay, so let's say I want to do this with my lettuce plants. And let's say I get data such that when I do the natural log of y versus t, my graph scatters around these points. Some plants are healthier than others. Some plants grow faster than others. But on the whole, it looks like we have something kind of like a linear relationship. Now, I like, and I will be asking on a test, that you be able to hand sketch a graph and then make your best estimate to what line comes closest on the average to these points. Now, disclaimer, you want to minimize the squares of the distances of the points, vertical distances of the points from the line, but I'm not going to ask you to practice for hours to be able to estimate the difference between finding the best, minimizing the squares of the distance and just minimizing the distances. So I'm going to say that this line right here maybe works pretty well. Okay? There are 4 points above the line and 3 below. But the 3 below might, on the average, be a little further away than the 4 up here. And we're actually looking at vertical distances, and I'm not getting into that, but that looks about right. Looks maybe close enough. Okay? Now let's say then that t has a scale that goes out to 80 days here. So that 40 would be here, 20 would be here, 30 would be here, 10, 30, 50 would be there. Okay, there are my 10-day approximations. Okay, now let's just say that I'm not even going to try to make this very accurate, but 4 here, 2 here, 1 here, 3 here. Okay, so what's the equation of my line? Okay, well, the line appears to have a slope, let's just say between this point and this point. If I do my fundamental triangle, I've got a run of 80 and a rise from about, I think, 1.3 up to 4. So the rise is 2.7. Okay, so slope of the line is 2.7 over 80. which is about 0.34, 0.034. The vertical intercept is about 1.3. So, natural log of y is approximately 1.3 plus 0.034t. Now this is all quite simple. If I give you a table of y versus t or y versus x, you can make a table of natural log of y versus natural log of x. Okay? So it's like you're going to have some numbers for t, some numbers for y. What do? Well, you make another table. You take your calculator or Excel and calculate the natural logs of y, and that's what you plot here. If it comes out a straight line, then you're fairly confident you have exponential growth. And we talked about this last time, okay? It could be that you have a power function growth, in which case you do a natural log of t and a natural log of y, and maybe that gives you a straight line, okay? Just to put it in context. Okay, in any case, in this case, we find that we got a pretty straight line. So we take our best fit line, and I prefer that you estimate it by actually graphing it yourself and drawing the line. Now your book tells you go to your calculator and do regression analysis. Fine, you can do that. I prefer that at least for several problems you draw it out yourself, because then you're not going into a black box of your calculator and doing something by pressing buttons that you don't understand. Then once you see how it works, sure, the calculator is going to give you the more accurate result. Okay? And that's the way you would ultimately do it. Or a spreadsheet. Excel will do that. Any online spreadsheet will do that. Okay, so anyhow, you have this model, and now all you do is solve for y. Well, you get y equals e raised to the 1.3 plus 0.034t. And that equals e to the 1.3 times e to the 0.034t and e to the 1.3, you're going from 2.7 up to about 7, and a third of the way would take you that far, and it's going up by 4, so maybe it's about this, and don't take that seriously. That's just I'm not thinking that hard on it. And even if I did, well, yeah, I could estimate that closer, but okay. And then e to the 0.034. Okay? That's about 1.034. That would be your exponential model. Now you'd have a pretty long doubling time for this. It's slow growing lettuce. Okay? So not a good model probably for lettuce growing in optimal springtime weather. But there it is. Not difficult. With a little practice, I think you'll have no trouble with it. Okay?